Hello, and welcome back to Old School Coding, where we basically are pretending to be living in 1992 again, and we are working on a simulator for a microcomputer system using the current best practices in the C programming language, which means ANSI C with a whole bunch of extensions that, for some reason, we know are going to become standard later on. So yes, we are building a simulation of a early 90s microcomputer system using a programming language in the early 90s and using the programming methodologies of the early 1990s. And if your experience with the 1990s was different from mine, welcome to the fact that in the early 1990s, it wasn't one big uniform community of software engineers. Without the, shall we say, close coupling of engineering communities we have now over the internet, there were a number of different schools of thought. Not that people tried to be different, it's just that you had a few people over here that worked out their way of doing something, and a few people over here who also worked out a way of doing something, and so on. So the styles you will see me be using are the ones that I picked up in Monterey Bay area in California, and then refined as I moved up to Silicon Valley to do more software engineering professionally. Salted, of course, with experience from my university experiences down in Santa Barbara. So that's the style of coding and the style of software engineering we'll see here. It's also heavily salted with the fact that I started out as a self-taught software engineer, self-taught programmer, who listened to the people around him that were professionals, but came up with my own ways of doing things. So some of the things you'll see me do might seem a bit odd, but none of them are too far outside the norm. As I showed later in my career, none of these things that I do were at all odd. They all are techniques that at one time or another have been deployed for various employers. So onward. I did a little more cleanup between sessions. I have forgotten just exactly how much of it I did on camera and how much I did off, but we do have a nice little system which is now implementing a bunch of instructions. I think the last thing I did was write some code that printed out all the instructions I wasn't supporting yet, and then I got rid of it because it was too much sugar for nickel, a phrase I didn't learn until well after 2000. Anyway, I put that back, and it's dumping to a file. And you can see in the upper left that when I do the build, I am actually printing out how many individual instruction opcodes I have not yet implemented. Now, there are some unimplemented instructions in the 8080, but we're at 107 to go. So it's probably, a dozen, I don't know. There's a column of 7 right at the beginning, and there's a few others scattered around. As we close in on that, I may set up a handler for those instructions to recognize them as an illegal instruction, so they will disappear from this unimplemented instruction code list. We may even use them as special trap instructions to cause the simulation to do something fancy. Who knows? Who knows? So the next thing to do, I took this list of unimplemented instruction codes, and I actually brought it into my 8080 document, and I set up a part of the document down at the bottom. It says, not yet implemented. And I started going over the list of instructions. So I've got the opcode and the assembly code for the instruction off to the right. And I kind of collapsed the ones together that were the same instruction or were similar instructions or related instructions somehow, kind of to try to work out what order I want to implement things in. I think I've got the next couple of things I want to do all set up here. That would be the LXI instruction, which loads 2 bytes. So the next 2 bytes in the instruction stream get loaded into a register pair. And I think I can get that done today without too much problem. It is going to require a bit of infrastructure work, though. So we have an existing bit of code called 2bops, which is the second byte of the operator. Now, 2bops comes in and says, okay, I'm going to run a machine cycle that reads a byte from the instruction stream and then turns control back over to the instruction. I would love to use 2bops for both of these immediate operands, but while most of this works, including the T1 and T2 doing all the right things and getting it incremented and all of that, the fact is that when we come out of the T2 or T-wait steps, we're ready to do the T3 of that machine cycle. We're diving specifically through CPU arrow M2 T3. Well, these LXI instructions want to do something different on machine cycle 2 versus machine cycle 3. So I need to have a way of saying I'm doing a machine cycle 3, which is going to call this other thing. Now, 2bops is working really well. So I don't think that there's going to be major changes to it. And any changes that happen to 2bops are going to happen to a lot of other things as well. So we already have the code duplication problem. You'll notice that in this project, we are fairly free about duplicating code and modifying it. This is a common practice from the late 80s and early 90s, which modern engineering now recognizes as being fundamentally dangerous. But with the scale of projects that we're going to work on here, I believe I can use this old coding practice and we can keep our eye on it. Keep careful, because we know in the 30 years that has passed that this is going to be a hotspot. This is going to be a bug. This is going to be a breeding ground for bugs. But we can deal with that. So let's do I-8080. Let's call it 3bops. So this will be used by some 3-byte opcodes. And I have just renamed 2bops to 3bops. And what I noticed here at the top was that the comment itself was wrong. So we're going to get into source 2bops. It isn't underscore B2, it's underscore 2bops. And third byte of multi-byte instructions. So T1 drives PC to IDL to address and status mread and sync high. T2 is going to drive IDAL, the incrementer, decrementer address latch in the 8080. We're going to take the +1 output of that and latch it back into the PC, release data and sync, drive DB in, wait for ready. And when we deliver control, it's going to be to M2 T4. Boom. There's our first significant change. Now, right now, we are not compiling because there is no such thing as state 3bops. So all these things that have 2bops, we need to set up a 3bops for them. And again, we're going to export. This is actually a T3 handler. So this is M2 T3 and M3 T1. This is M1 T4 and M2 T1. Let's make those explicit so that when we're reading through the source code, we know what's hooking up to where. Okay. We know that we need a M2 T3. We also need a M3 T3. And this will be picked during M3 T1. Is it though? Is it though? So we will be picking from the M3 T3 or M2 T3 during the T2 cycle. Not important, but if it's important enough to comment, it's important enough for the comment to be correct. So it's picked using IR. Oh, come on. picked from using IR during M2T2. There's our M3T3. So we've got 3 bops. 2 bops becomes 3 bops. M2T3 becomes M3T3. And now we need to set up the support for it. And what I notice here is I also forgot to set that. Okay. So you notice when we duplicate code and we edit, we're also catching errors in the original code. So we're back to compiling properly. So 2 bops gets initialized here. I'm going to add in 3 bops in it right here. There's no more 2 bops. The other is M2T3, which we need to have an M3T3, and that's all of that for those updated operations. So now we have this warning that we are not declaring 3 bops in it. How about that? Well, goodness. Inc. I8080 impl. There's 2 bops. So now there's 3 bops. And we're back to compiling. So some of you may notice that this loop that I'm getting into, where I start implementing things and I get them to compile and then I get them tested, it's starting to have a whiff of test-driven design. That's because this is kind of the same way to do things, where you want to write some code, but you also want to make sure it works. And we have been doing that for long times. I started doing that, my goodness. When did I first start writing code? The first program I ever wrote, I could type a number on a teletype and it would print back its square root. And I wrote this in Fortran on cards by reading a manual. I literally was reading the manual for the SDS 9300, and it's extended Fortran 2. And I had read up through the sections of it that actually defined what the Fortran language looked like, but I hadn't yet read all the intrinsic functions, so I didn't know there was a square root function. I held on to that card deck for a long time, as some of my friends thought, oh, you're keeping your first program because you're proud of it. No, I'm keeping my first program because it reminds me to be humble and read the entire frickin' manual before starting to assume that a particular way is best. Anyway, but even with that, there was the idea of you write some code and then you exercise it to make sure it works. Okay? Now, I didn't have automatic testing, obviously, back when, a deck of cards this thick is one printer page. Well, actually, a little bit more than one printer page, but you get what I'm saying, is that a fairly modest-sized bit of code turns into a physical artifact that is significant. So no automatic testing. But later on, as I got into writing code that didn't exist as physical cards, there was always the idea that I'd write a function, and then I'd write some code to make sure it worked. And I wasn't the only one. I picked this up from other people that were doing it, so it's not an uncommon practice. Anyway, how are we going to test 3 bops? We're going to test 3 bops in the field of fire. We are going to write some code that uses it, and if 3 bops works, we're going to assume it's correct. Same as 2 bops. We still don't have adequate testing for 2 bops. Anyway, so 3 bops. I want to make sure we're actually getting into this. So I'm going to put in a print top right here, just the print top. I just want to make sure, and we are in fact getting into there. So that's my testing for 3 bops. Make sure that we're calling it. Because once we've got 3 bops going, it's just like 2 bops. We already know that 2 bops is working. We're a duplicate of it. Let's make sure this is fresh in my mind. PC into IDAL. IDAL into adder, status mread and sync. Step into 3 bops T2. 3 bops T2 on the next cycle does IDAL +1 into PC. High impedance on data. Release sync. And now in reality, I should be releasing the data to high impedance after I release sync. But data Z, there are no edge triggered effects at data Z other than what we're using to do signal tracing. So that shouldn't matter. So we switch from outputting sync to accepting our data in. And then we either wait or M2 T3. This is wrong. This is M3 T3. This is why I go over these things carefully. The cat is sneaking behind me. I don't know whether she's headed elsewhere. So this gives us now the 3 bops, which we can call up, and we can either say, do state 3 bops, which is going to be the last T state of the second machine cycle, or having done something in the last T state of the machine cycle, we can actually do this. We can actually just call up state 3 bops T1 for the T1 of the next machine cycle as we wish. So what are we gonna do with this? Well, let's start on our LXI stuff. So we need an init, and I am going to toss LXI init right down below MISC. In fact, I'm going to take all the MISC stuff and I'm going to duplicate it and have an LXI. Okay, so we are now hooked up. We have declared our init, post, and bist. And now we're going to call init. We're going to LXI init after we MISC init, and that's the only one. We get into test, and we get into i8080 test.c, and we want to do an LXI. This is a little more complicated because we want to do more than just duplicate the one line. So now we have these calls that are inserted in our code, but it's not going to work because we don't have those calls quite yet. So who is our best candidate for these things? I'd like someone that has nice comment banners already set up. Actually, InkDeck, I think I put the banners in InkDeck. Yeah, okay. Oh, I didn't finish editing InkDeck. I did not put the comments in. Oh, I'm a naughty boy. That would have been caught in a code review, which we did back then. And we really reviewed code. But yeah, this doesn't actually have... Oh, right, my test code is somewhere else. So, the things that are missing are init, post, and bist. Well, let's start off with init. So pound include i8080 impl.h. We're going to end up just typing this. I sometimes search my source code for instances of the word to do, so that will help me remember to do something. So, void i8080 LXI init, and that does indeed take an i8080 CPU. So we need to implement there. I'm going to toss an abort in so that when we do get there, I'm going to start aborting when I get to code that absolutely needs to be implemented. I should have been doing this all along. Now we can go into test i8080 LXI test.c. And let's look at inkdeck test. I'm going to need clock.h because I'm going to be clocking things during the testing. I need the 8080 impl.h. And again, I just put 3 dots out here. Yeah, I could grep for 3 dots, and I probably will, but I sometimes use those in context that it's not a to-do, so I need to actually write the word to-do so that I get into this stuff. Now, just going to grab all of that stuff, and any of these guys that are leave one line. I'm going to leave that guy commented out there. This is void ts to do implement. Post, I will leave post as a just do nothing for now, but I will put in to do refine bist into post. There's several other modules where I have literally no post, and I have a significant bist. I couldn't see a way to make bist any slimmer to go into post. Now these guys, I think this is the rest of the file, but I'm not sure. Yes, it is. Okay. So I now have methods for bist and post. Okay, so we declared a bunch of things static that we did not then define. Redefinition of i8080 ink post. That's because I didn't fix the name here. LX, how about I do the right thing? LXI, there we go. So now this will run, and it's going to abort the first time it hits one of these lines. There, now I know where I am. So I tossed a bunch of aborts in during this process. And apparently, I goofed. Because I should have gotten something over here that said where I was. So we are getting into these guys. When I comment out the aborts, so print top is not flushing its data output properly. What is going on with that? So print top is only printing to standard output, not standard error. Oops. So if I want to mark that I've gotten to somewhere, I do need to have a stub. So what I'm going to say for these guys is stub. Actually, I'm going to use fail. I believe I have a fail macro. Yes, I do. It's a stub followed by an abort. To do implement. There. So now we have that. So we have not only the message and not only the abort, but we also have something where I can just hit a function key. We go right to that error that says we are not implementing LXI in it yet. Okay. Okay, so what does LXI do? Let's take a look at the PDF. Bink. Magically appears in OBS, and now I need to magically make it visible on my screen properly so I can see it. So LXI is down here, and M1T4, it basically does nothing for one cycle, but it does turn control over to two bops. And that's the same as all the other stuff. Not all the other stuff. It's similar to these other guys that have a two bops, that have an immediate. Let's use MVI as our comparison. So MVI here has a do nothing T4 and does this. So we are just like MVI, except we are going to be doing 2 bytes into 2 registers. So LXI is MVI on steroids. Okay, so source. Where is MVI? MVI, I think, is right there. So really what I should be doing here is grab MVI, and I'm going to come over here and I'm going to copy it in, and I'm going to shave it a little bit. MVI becomes LXI, 2 bops, becomes 3 bops, and we're going to do a little bit more work. So LXI is manage LXI instructions. It's going to manage all of them. So what I want to do is define a LXI instruction for that falls into M2T3. This is going to be the instruction that receives the high byte. And I will just name it based on the byte that it stores. So B, D, and H. And let's make sure that the LXI does do them in this order. RL followed by RH. I'm glad I checked that. So C, E, and L. C, E, L. And LXI also has SP. So this will move, well, let's do it by register pair. B, C, D, E, H, L, SP. Okay. DDD becomes RP. It only goes up to 4. It's LXI M2T3 of RP. All of them are set. Opcode is LXI is 01 hex with the RP left shifted by 4. We're going to have M1T4 is going to direct me to 3 bops. M2T3 is going to send it on into M2T3. But we also need M2T4 here. I'm going to have to rewrite comments. Not M2T4, M3T3. There we go. This is M2T3. So this is a RP. Oh, the stack pointer is going to be a bitch, isn't it? Almost makes me regret that I didn't organize my registers using a union of these so we could have a BC register pair, which is an address, and a B register, which is data. When you modify the data, it modifies the upper or lower byte of the address thingy. So with that in mind, these are just the lower byte. I'm going to call it P for S and P. And these are the upper bytes. Okay. Which means that my macros for S and P are going to have some special code in here to merge the data properly into the stack pointer high and low. How are we doing here so far? Used but not defined. Defined but not used. That's fine. BDHS, M3T3, bada bing, bada boop. And now what I want down at the bottom is I'm going to end up with impls where I had definitions above. I am keeping this comment, again, because somebody could be just grabbing this file, looking at it, and then saying, why is he doing that? You don't need to have a declaration. Well, it's because I want this to be syntactically correct without confusing the indenter. Okay. So, during M2T3, first of all, we don't do a red M1 init. We're going to do that in the other one. Let's make a copy of this for M3. Because M3 keeps the red M1, M2 does not. Okay, there's another difference between this and 2bops. Nope, that's correct. Okay, so 2bop, we don't use 2bops. We're going to be 3bops. This guy gets this one. This is correct. So we are writing to the low byte. And the difference here is that for P, data 2, this is going to have to do a little bit of a dance. There is no P register here. Like that. And this guy is going to have to do something similar. And that's bad. The indenter really had a field day with that one. So for some reason, getting down to here, oops. And now I've got somebody that wants to chat. Hold on. So, the real reason why I always pick up the cat when she's meowing at me is not just because you never regret time spent holding a cat, do you? But when she's doing that, I literally can't think. So, the reason why the indenter is confused is because this construct that I've got my mouse cursor on right now is not legal C. I need to expand that name macro manually so that the indenter will know that it's looking at a function definition, not something really weird. Like I said, this is the old Berkeley indent, which has been maintained by the GNU project, or a variant of it has. And she's going to need a little bit of cuddle time here. I suspect she just finished having her breakfast and then going outside and enjoying the patio for a bit. And now she's ready to get some rubbins. And after she gets some rubbins, she'll want to go crawl under a blanket somewhere. Is that right? You gonna look for some blanket time? So basically I just need to expand these macros. So what I could do with one hand is grab that, come down here and paste it in there. There's that name. I can do some editing one-handed. Okay, so we do that, and now we compile without errors. We start running and we get to do implement, and this is compiling, and it is running up through the point where we get to that to do. Okay, now you're just falling asleep on me. I am going to go tuck the cat underneath something. I'll be back. So, it's a really good idea generally for a software engineer to have a dog or a cat or something else that can distract their attention unpredictably. Because if you have to take breaks. If you don't take breaks, your coding suffers. So even with interruptions and the fact that they do induce bug states in your code, it's still better than just working straight through. Okay, so there's LXI. And we have implemented functions to load the low byte from the first instruction And this needs to redirect us to the second instruction. So I did not name these properly. I need to put in RH and RL into the macro so that I can have this guy know the name of the other guy. So we're going to have RHRL. So we're going to now change R to RH, token paste RL. And now where we use it is going to be a syntax error. And B, comma C, D, comma E, H, comma L, S, comma P. Same thing here. Oh, come on. That's RL. This guy's got to move into RH. Now, the reason I did that was so I could put in something here. Well, first of all, let's write this one. CPU arrow next state is equal to I8080 state LXI M3T3SP. And up here, this is now M3T3 RH RL, just like that. Why is this indenting so far? Struct S8080 has, oh. There we go. So now we're getting to implementing the BIST. Let's do a quick once over with our eyes again before we start the test. We have some M2T3 state control functions, which are named after the register pair in the instruction. We have some M3T3s, which are also named after the right stuff. Now, this guy is going to the wrong place, I just realized. I need to head back into 3bops. So 3bops has T1, T2, TW, but 3bops needs to provide M2 and M3 versions. M1 T3, M2 T1. So that's M1 T4. So we're not going to have that. So we'll have an M1T4, which just sets up for a 3 bops M2T1, M2T2, M2T wait, which will after TM. Okay, so M2T3 comes from CPU M2T3 IR. And then we dive back in M3T1, M3T2, M3T wait, and this brings up M3T3 of IR. Okay. M1T4. So 3 bops M1T4. Who needs to know about that? The person that needs to know about that is us. Nobody else. Well, no. Okay. Instructions will need to know about M1T4 and M2T1 and M3T1, so they can direct their control flow. This is 3 bops M1T4, M2T1, M2T1 does that and dives into M2T2, which does this. M2T2 does these things. It dives into M2T3 here, or into TW. This is actually, I need to keep it separate. This is a M2T wait. And down here, we dive into M2T3. Now, all these guys that are for M2 need to be duplicated for M3. So I wasn't done with 3 bops. The reason why they're duplicated is just so I can use this table properly. Knowing our machine cycle number, we could have folded these together and used an additional direction. That costs time. So I'm just going to stick with my idea of lots of little teeny functions that know how to do something fully decoded, even if they're trivially different. Now this is not going to compile because I've changed the names of some things in i8080. Let's go here, i8080.c, inc i8080.h. 3 bops has several different handlers. M1 T4, M2 T1, we couldn't use 2 bops because 2 bops would set us up improperly. Or did it? Let's take a quick look at 2 bops and see if I can eliminate the M2 cycles from here. So if we used 2 bops for the second byte, we would land here. We would then dive into here. We would then dive into here, maybe here. And okay, so we can use 2 bops for the second byte. I think that's where I was going originally. Why I forgot that, I don't know. But that means that 3 bops does not expose an M1T4 or an M2T1 anymore. It does expose an M3T1. So we don't actually get into 3 bops until we're ready to do the M3T1. There we go. That's simpler. I think that was my original thought. I'm not sure why that faded from my head while I was coding. So we're using 2 bops for the second byte and 3 bops for the third byte. Now, is there anything these guys do which precludes us doing this? Well, let's see. We are getting to M2T3, which gets us back out to our decoded instruction. We are not declaring the end of a machine cycle here. I think we're good. Okay, so this guy, we're setting M2T3, so we're going to use 2 bops. So 2 bops is going to direct to this LXI M2T3 of whatever. So at the end of the second machine cycle, we're going to get into our code, which is going to direct us to 3 bops. M3T1. Okay, so then we get into the third byte of the operation. PC, IDAL, data, all this is the same, bada bada ba, and we end up going M3T3 here and here. M3T3 gets us back under control here, where again we are doing the high byte of the register pair, and we are declaring the end of the machine cycle under the instruction. So the next T state is going to be the start of an M1T1, and that's good on both of them. Notice that all of our wait logic just keeps getting copied forward into new versions of this code. So struct S8080 has no member S3 bops. So really, I don't need to have M3 in any of this stuff. So we did a state 3 bops T1. There we go. And here, those have to have the M3. This does not. There we go. So that other little loop that I just did of duplicating some code, looking over it to customize it, and then eliminating it because there are literally no differences, that's also not an uncommon path. But what it does do is gives you a chance to look over the code that you are now reusing, code you are now sharing, and make sure that it's actually appropriate for both uses. So now if we get into LXI, let's go through this again. LXI is going to decode to please use 2 bops. 2 bops will get the second byte and call into our M2T3 here. We will then direct to 3 bops, which will get the third byte and call into our stuff here. So what are we doing here? Low byte is end wait, move into low, terminate DB in. Next is 3 bops. That's correct. And we have to write it manually for the stack pointer, which, almost forgot. So what we want here is unsigned. I'm going to have a pseudo register called P. And we're going to adder 2 of CPU arrow SP is actually, let's make this explicit. We have SP and we have P. And we're going to do something similar for the high byte. Almost goofed there. Unsigned S and unsigned SP. Okay, good thing we did that quick spot check. We now have S implemented. So for most of them, it's data to RH, and for S, it's grab the data, merge it with stack pointer, and dump it in. That's correct. So now, let's actually write some tests for this. Test I8080 LXI test.c. And I want to pattern this after the most recent set of tests, which has all the most recent set of tools. So the pattern looks something like this. When we come in for the top, the CPU is reset. So I don't need to reset it. I'm not going to be running several subtests, so I don't need to reset before each of the several subtests. So we're just going to do that, and I'm going to copy in all the way down here to where we actually start doing something. We'll replace that something with the right stuff. We are interested in B, C, D, E, H, L, and SP. And our test program is going to start out with op-nop. I like having a nop first because I may want to widen my signal plots just a little bit before the first instruction, maybe. Sometimes I do that. LXI, BC, 1, 2, 1, 2, 2. 3, 4, 4. HL is 5566. SP is 7788. And we're just testing LXI, so there we go. I may also implement the DAD instructions in here if this implementation turns out to be as small as it looks. BCDEHL SP. There's the program. Our initial state is everybody is going to be in the Z state on the plot. and it's low, comma, high. Oh, thank goodness for the conversion errors. And success is unused because we're not doing anything with it yet. Let's go grab a sig plot real quick. And this is ALU LXI. Actually, this is just LXI. Now, I'm going to set up a whole bunch of these one instruction thingies, which are, as a comment, going to have what the instruction is. And 3 dots. Haha. Careful, Greg. These two need to be reversed, so it needs to be low byte, high byte. And I want B to get 1, so I need to swap those. Reminder, operand for LXI are little endian. Because when we write numbers naturally, in the English-speaking world at least, it is most significant to least significant digit going left to right. However, when we store data for the 8080, we store the least significant byte followed by the most significant byte, because the 8080 follows Intel's evil idea that you should put low bytes first, little endian. I am a fan of big endian architectures from the moment I saw my first big endian CPU, which I believe was the LSI 11. For obscure reasons. Basically, my dad ran a computer lab for the Navy, which had a collection of computers. It had the big SDS 9300, and then they installed some PDP-11s, which was a DEC machine. And I seem to remember that the LSI 11 was big endian 16-bit. I could be wrong. My memory could be failing there. I do know that when my professional life got around to programming Spark and later MIPS, the big endian was ever so natural. And for those of you that say, oh, but Greg, MIPS is little endian. Well, at Silicon Graphics, when they owned MIPS, we did have the ability to switch the processes between big endian and little endian. And in little endian mode, we called them the SPIM, S-P-I-M, because it was MIPS reversed. Pain in the tuck. And let me tell you, even though you put it in little endian, there are still some aspects of the CPU that had to be big endian. For instance, you're fetching instructions. You're starting up. You haven't established little endian mode yet. Oh, what are you going to do? Anyway. So big endian on the assembly code input and little endian on the byte output. And there we go. So now we put in our thingies here. I-8081 instruction. So the LXI instruction, let's make sure it does not modify any flags. It obviously shouldn't. This data is not going through the ALU. But I'm going to bring up the definition of it really quick. I haven't turned on the PDF onto OBS, but LXI, where did you go? was a time when I had a very strong intuitive understanding of the order in which Intel displayed their stuff. Okay, so LXI, oh, that's INX. There we go. So LXI, turn this on, down here in the corner, load register pair immediate, byte 3 is moved into the high order register and byte 2 is in the low order. And you notice that even the way they discuss the instruction is big endian first, and they have to show little, low order first here, and they have to show that the offset is that way, but they have to discuss it high to low. Because human beings think most significant first. Thonk. And of course, no flags are modified. Okay, got that. So now we can start comparing some things. So 1-1 is the B register. This is 7788 is the SP register. Let's fix these up. D, E, H, L. 1 1 2 2 3 3 4 4 5 5 2. Get this right. 3. And I'm going to run one more knop in the plot, and there we go. So this plot's going to have a knop at each end. LXI instructions. We are not doing anything with flags. So this test condition is failing right here. So the actual value I got for SP was FF88. So my 77 didn't do the right thing. And that is because I did a right shift, and I didn't do a mask, and for some reason it said, oh, I'm right shifting a byte, so at some point it sign extended it. So data, I wonder if I may have defined this, I may have defined data to have a signed value. Let's take a look at that. So data is defined as containing a byte. And byte is indeed defined to be a uint8, so it should not be sign extending P. If this fixes the problem, then I have goofed in my understanding of what happens when you read a uint8 into an unsigned and do that operation. Wait a minute. That FF came from the fact that it was high impedance, didn't it? Yes, it did. I think we may just not be getting all the way through here. So I am not going to put that mask operation in because I strongly believe it is unnecessary. I am, however, going to look at the plot. So doc, image, we are looking for LXI. LXI is not being printed because we did an abort. Let's turn off the abort. So a couple things are happening here. First off, we're getting a test condition failed that looks like we're not running all the way out to the end of the world. Like we're stopping before the last instruction. Oh. No. Red M1 int is being set in these two and nowhere else. And this is executing 7.7 as an instruction. This means that we are not getting in. Oh, look here. I have the wrong next CPU state. There we go. So we were trying to execute the 7.7 because we were not doing it. And there we go. We're done. And now I can look at the LXI picture. So this is what the timing diagram looks like for these LXI instructions. So 0, 1 is our, well, we got our NOP in here. We got our LXI, which has 3 machine cycles. And we get 0, 2, we get 2, 2 into C and 1, 1 into B. That's correct, so 1, 1, 2, 2. Same pattern for DE, same pattern for HL. And SP changes to FF88 and then 7788. So LXI is now working. Okay, that was quick enough. I think DAD. What do I want to do with DAD? DAD is definitely the next instruction I want to do. I could toss it. I could toss these into MISC. Yeah. So, DAD. There's 1 for each register pair. So we are going to go back to LXI, and we're going to have something similar for it. And we're going to use this same thing where we're giving the 2 registers in the register pair together. So looking at the PDF, unfortunately the PDF is actually a bunch of scanned pages, so I can't do a search for text. So, hey meow. So DAD says add register pair to H and L. Content of register pair RP is added to the content of the register pair HL. The result is placed in the register pair HL. Only the carry flag is set, and it's set if there is a carry out of the double precision add. So carry flag is set based on the output of the high byte. So what we're going to do is we're going to add the low bytes and store the result. Then we're going to grab its carry and add that carry into the sum of the high bytes, store that, and then update the carry flag. Take the PDF off of OBS and slide it out of the way. I need to check the timing real quick, have that in mind while I'm doing this. DAD DAD actually takes 3 machine cycles. That's interesting. Because, let's look at it. This is a more complicated bit of internal logic than I thought. So here's DAD. So M1T4 is a do nothing but deliver control to us in M2T1. M2T1, we have R low goes into accumulator temp. During M2, we get the L register. We can't have 2 different registers moving across that data bus. Remember, we've got a single 8-bit data bus out of the register buff, or out of the register bank. So M2T1, we set ACT up. M2T2, we set temp up, and the ALU forms the sum. M2T3, we then write the ALU value back into the L register and update the carry flag. At M3, we do the same thing for the high byte of the register pair, and we do an add with carry. Very straightforward, but it is going to take us 3 machine cycles to run. So DAD, well, there's a standard decode for DAD M1T4. And I'm going to need a decode for M2T1. So make sure we have it. Yep. No, we don't. So we need a M2T1. Well, no. Instead of doing an M1T4 that uses another indirection to get us to M2T1, we'll have a DAD M1T4 will be this guy. So DAD, can I DAD SP? I can DAD SP. Okay, so we double add BC, DE, HL, or SP into the HL register pair. So M1T4 is going to be these guys. Oh boy, and DAD is going to involve a lot of bits of code, so let's not put it in MISC. You can get rid of a lot of stuff here. Okay, so M1T4 is going to trigger M2T1 to do the right thing, so we need M2T1. We're going to need M2T2 and M2T3. And then we're going to need functions for M3 as well. Lots of little teeny functions which are going to be doing some very small very controlled things. Do I have that right? M1T, so M1T4, work through it in our heads, does nothing, but arranges for the M2 cycle to start doing work. M2T1, if we look at DAD, make sure I've got that here on my screen. M2T1 reads the low register. M2T2 is going to set up the ALU input from the L register and temp and form the ALU output. M2T3 stores the low and arranges for M3. So yes, all those little bits of stuff do indeed get needed. So DAD and it gadonk. The operation is 09 hex with RP in the top bits. We set that to state underscore DAD M1T4. And each one of these functions does something unique and then passes control to the next function. The SP functions are going to have to be handwritten because they operate on the top and bottom half of SP. I am even now more wishing that I had organized my register bank as something where I could union the 16-bit and 8-bit quantities. We're going to need impl macros. So M2T1. So focusing just on M2T1, hold on. I forgot M1T4. Easiest way to do this is just to take this and duplicate it. Okay, so M1T4 is going to do nothing, essentially. We do need to rise the weight, I believe. Yeah, anytime we have been reading, we need to raise the weight stuff to say we're done. Hold on, M1T4 doesn't do a weight, doesn't do that. Right, M1T4 does nothing except set state next to name M2T1 of RHRL. Okay. we're going to get these errors on SP as we implement. M2T1 is a T1 cycle, which is not going to do any of this stuff. So let's start by just getting the macros set up so that they chain properly. In fact, just like that. And we're going to break SP out at this point already. Because from here on, we are manipulating the stack pointer. So, a bunch of warnings about defined and never used. So we can start breaking this guy down too. So duplicate this from M1 to T1 to T2, T2 to T3, of course the state next need to be manually intervened. And then we go back up to the top and we get the M2 stuff, duplicate it to M3. And this last guy needs to turn control back over to the next instruction. So this is ret M1 int. Okay. Name M1T3. This is from M2T3. This is M3T1. Oh boy. Cross-check these next states. So M1T4 goes to M2T1. M2T1 goes to M2T2. M2T1 goes to M2T2. Two goes to 2-3. 2-3 goes to 3-1. 2-3 goes to 3-1. 3-1 goes to 3-2. 1 to 3-2. 3-2. 3-2 to 3-3. And this guy just hits M1, ret M1 int. Boom. compiles, runs, has to-do items. Doesn't do anything yet. So here I could actually write the DAD test code and see that it does nothing. So I'm going to take the LXI test, so what we're going to do here is I'm going to do the same set of, well, actually we can initialize the data to the proper values here. So I don't need to see us doing LXIs. And these comments about test timing being a bit odd, now that I've got this one instruction thing, it's not that odd and it doesn't apply here. So I want to set these up so that as I do the DAD instructions, HL goes through some well-defined transitions. So I'm going to set up H and L. These guys are, well, yeah. What I'll do is I'll have each one of these be a single bit. And this SP will be 8040. So 40 in the low byte. So what should we be getting? HL is going to be B, C, D, E. Oh, that's one is in the high byte. Okay, so 4080 for some consistency. So BC is OX0102. DE is OX0408. HL is OX1020. Okay, so when we DAD BC, we need to test the carry thing. I want to set it up so that when we finalize it, I know how to do this, 80, 40, 40, 20, it is I want, when I do the, when I add DAD SP, I want it to get the carry out. So each one of these, as I DAD it in, is going to kind of accumulate things forward, so these all add up to what I want. So BC, this is going to be, let's test HL first, 4020. So we're going to add BC, we should get 5028. When we add DE, it's going to add, this is 70. DE is 10, so this is going to be 38. We're going to add we're going to add HL to itself. So this is E0670. We add the stack pointer in, it's 8040, so 8 plus E is going to be 6 with a carry. And instead of NOP, let's use XRAA. Which is my favorite instruction for clearing the accumulator. I think it was 46 was that value. And carry bit is the low bit of the flag word, so there we go, 47. Now if we run this, I'm not actually running the test yet, but we compile. So where we have LXI, I want to duplicate it and change LXI to DAD. And then I want to stop for a moment so I can do some editing. Okay. Okay, so now we're going to get a whole bunch of test condition failures. And the interesting thing is that we are ending up in an illegal instruction with value 09. At PC equals 2, 0, 1, 2. So DAD DE did not get set. T4 of op. We're not calling a init function. We are not calling the init function. Right. Because I didn't put that line in right there. So now we have test conditions failed because the values are not set. That's good. So you notice that all of these guys are saying expected value is 46. Whoop, 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 whoop. XRA should be working. Right. I have to step forward a few more clocks because XRA doesn't commit its results until T2 of the following instruction. So now we have failures on H and L, H and L, H and L, H and L, and flags. So now we need to do the implementation. So M2T1, we are copying the low register, the selected register, into ACT. And for a stack pointer, now I'm going to not mask it because the masking happens as we do the conversion of the data type. During the second part, we are putting the L register into temp. So CPU, arrow, oops, data. No, the L register, not the low part of the input. And we're also setting the ALU to the sum. And my auto indenter wants to indent underneath there because I'm a bonehead. I need to avoid indenting that manually. ALU is going to be equal to what is going on here? Why did I not? There was a trick I used to keep that from happening. I wonder if it's just, yeah, if I just have that, if I have that declaration there, it's going to be a bitch. So data to CPU there, ALU. And I need to do something with carry. I really do. If I open up braces here, is the indenter going to be nice to me? Signed ALU is equal to that. Yes, it is going to be nice to me. Amper equal not flag Z, not flags. So LXI, let me double check that DAD only affects the carry flag. Only the carry flag is affected, which means, yep. we go. I'm going to set this off just a little bit, because this is really our ALU doing work. We're going to do the same thing here. Knowing that the hard part for SP is going to be peeling out the low byte and the high byte, and that's not very hard. So data to CPU temp is CPU SP value, which is just going to get the low byte. Oh, her to her. The hard part of this was actually done up there. So the only real difference between these two is where we're going in the end. So since we are not actually operating on the stack pointer register in this guy, we don't need him. In fact, the only difference between these four functions is where they are going. Which I could eliminate eventually with a single memory indirection, which I would rather not do. I would rather have extra code than add one more memory indirection to my inner loop. Okay, M2T3. Back to the timing diagram on the right. I keep this far to the right on another screen so I can see it. It's not useful enough to have it here. So M2T3, we are taking the ALU content and writing it to the L register and to carry. So M2T3 also does not need a customized version for the SP because we're done dealing with SP until the next cycle. So M2T3 logic is data to the L register is CPU arrow ALU value. Now with that in place, we should have seen some of our test conditions change to passing. And indeed we do. We see that the L values are now correct, except down to here, where it might be that I did bad, my math bad. Yes, we had 7-0 in HL. We add the stack pointer, which has 4-0, and this does in fact become B0. SP low is, hold on, 4 and 7 is 11. Sorry, a little slow today. So we're down to 5 failures now because we now have the proper value coming in the L register. So now we work on the H register. M3T1 is where we get the high byte of the operand. It's going to look a lot like M2T1. let's just grab this bit. Actually, let's just grab that. So M3 T1 Phi2 rise reload ACT from RH. Which means that we need to do something special for SP. High byte of the stack pointer right there. During cycle 2, a lot like this, but it's going to operate on the high byte. It's going to be an add with carry. So we get the H value into there. The ALU is going to be that. In fact, I'm going to defer writing to ALU until after I write to the flags, since that allows me down here to say if CPU error of flags. Oh, now I'm using flags in several places, so let's give it its own. I do not know why that wants to indent that there. But I think what I need to do is have a decal. That's how I got around it. Yeah, that looks better. Why? Oh, sometimes juggling the macros so that the indenter in Emacs is happy can be quite the pain in the butt. because it does take some clues from some other things. So we're going to go to previous line, put a backslash. Here we're going to put 4 spaces to front. We're not going to allow the auto indenter to do anything until we're done. So now, what confuses the auto indenter? I think we are good. These. Not sure why it's not lining up all the backslashes. I really am not. Being a little quiet here because I'm trying to work out why this is not indenting the way I expected it to. Statement nesting error. Aha! So I have an extra brace in here somewhere, right here. Right, because I eliminated the braces around that. That's why we were confused. So if that's the way indent indents it, what I want to do instead for Emacs is I want to put it in the macro. Go to the end of the previous line, backslash. This line gets spaces. Now we let the indenter in the editor iteratively break this down, and I come up with that. Could it be as simple as Emacs indent not wanting to look at the indenter itself wants to work very locally. Okay, so it wants to look at the current line and maybe the lines above it and below it. And it's entirely possible that completely blank lines are going to hose it. There we go. So it's the blank line thing. So we're going to take H, put it, the high register H register into temp, and then we're going to add them together and move on to the next. That's correct. And now we want to do something similar for SP. This cycle does not actually deal with RH or RL individually, does it? No, it doesn't. So M3T2 is done. Ah. There we go. So let's use this construct in the other. Keep it consistent. Again, let's eliminate the blank lines because my editor is not clever. Again, I could load up all sorts of things to have Emacs look out to an external tool that parses the C code and does the right thing, and it would probably do a much better job of indenting. But that wasn't what I had available at the time, so we're not doing it. M2T3. Okay. Now M3T1. M3T1 grabs RH into the accumulator temp and the high byte of SP, so we got up to there. M3T2 does the work. M3T3 is now going to be just like this guy. Ready to H. Now I am actually committing the carry during the T2 cycle instead of the T3 cycle. And that's because I don't really want to defer this. I could get it done in the right cycle by deferring the ALU work. Do I want to do that? Yes, I want to do that. So this bit of work here gets moved from M2T2 to M2T3. Actually, it has to happen twice. So during M2T2, we want to commit the result to the ALU, but not to the carry flag. And during M2T3, we already have the result in the ALU, but we need to recompute it so that we can pick up the carry flag properly. All because we're not carrying more data than we should. Now, one way around this would be to have the ALU output be wider so that it would have the carry bit in it. But that's not part of the CPU state now, is it? Or is it? Perhaps the output of the ALU are the flag bits that haven't been committed yet. It starts getting too complicated. Let's just do this. So M3T2 now has the work it's doing. Oh, the other thing was we didn't need to have our nested scope here. So M3T2, again, we do not want to commit to flags here. That does mean that we need to grab this stuff, copy it down here. Still don't know why this is not properly aligning. Okay, it is. Okay, so search reverse for backslash new line. Beginning of line, indent me. And that goes up by ones. So apparently this one line is long enough to cause problems. Well, we know what to do about that. This is the only place we are using the flags here. Oops, M2T3, no it's not. There we go. Redefinition of M2T3BC. There we go. Make some errors in my M3T2. So we are down to two conditions failing. So after we DAD SP, this is saying that we are receiving E0 instead of 60, which means that I did not do this guy. So that, except that oh, this doesn't actually talk to S or P. There we go. So Next thing is, do RH and RL appear anywhere in this macro? They do not. So really, M3T3 is common across all of them. They're the exact same code. So I could share an M3T3 between them, but that's a very small win, and it makes it inconsistent. So we're just going to keep it as it is. We have our double adds going. It's more code than I anticipated it being. I was able to use macros to keep it from being too horrendous, but it's still, even with the macros, it's more code than I really wanted. But it works, and it's passing our tests, and it is indeed setting the carry flag where it should. We did not exhaustively check that it leaves the rest of the flags alone, but for that I can count on looking at this by eye and seeing that we are indeed doing OR with the carry or AND with not carry. We didn't have a condition where we are, for instance, adding something where the carry out from the low byte causes the carry out from the high byte. But I think we can. Do we ever get into that condition? We may not be exercising this bit of condition at all. Yeah, let's do that. So now we have some errors. So now our sum here is A0, and our sum here is B0. And our sum in H is now going to be E1 because we had a carry out. That checks our carry out right there. And this 7-0 is now a 6-0. This guy is 6-1. And this is now E0, is that right? Yes, that's correct. There we go. So now we're checking also that the carry flag is handled here. And I'm going to just do that. And I'm going to eliminate the flag variable from there. So there's DAD. Let's take a look at the plot. So this is our double add test. We start with valid data in BCDE HLSP, which is all set before we start the plot, so that it doesn't show here. SP is marching across. The accumulator gets cleared to 0. Here's our ret M1s. Notice our NOP is very much shorter. These guys are long. These M2 and M3 cycles are non-memory cycles. We're not referencing memory at all. So, yeah. We're not even doing a sync. I'm double checking that. But yeah, during M2 and M3, this guy is not issuing status output. Because it's not doing any sort of operation. There is no status for internal computation. There's all the statuses have to do with what kind of an M1 cycle it is, and so on, or what kind of a machine read or write to memory. So that's LXI and DAD, and I think that may be enough for this session. Let me bring up my Get Kraken real quick. There it is. I made it long because it was on my other screen. Let's shorten it up so we're just looking at it here. So net changes. I edited this and didn't commit it yet. This is the list of instructions that are not yet implemented. And I can actually adjust that now. Just going to move that down. ALU, this is dad.png, and this is LXI.png. And if I turn on the inlines, we see it there. There's DAD, and there's LXI. And we go back to get cracking, and we now see this and the fact that I added those instructions. So stage the file. i8080.h. We changed the comment on the 2-bops stuff to say specifically M1T4 and M2T1. We added the 3-bops M3T1. And M2T3 picked from using IR during. Okay, so comment changes there. Implementation, we added 3-bops, LXI, and DAD. README, we added those too, and I haven't commented them yet. We'll add comments offline. Initialize 2-bops and 3-bops. Initialize M3T3. 2-bops got some adjustment. Fixed its comment. 3-bops was added. DAD was added. Ink deck. To do, right? Good comment. Yeah. LXI got added. Support, let's discard that hunk. Let's go back to aborting when we get a test failure. DAD test was added. Ink deck test was to do, right? Good comment. LXI test added. 8080 test now tests LXI and DAD. Commit and push. And I will separately add comments. So you see we're beginning to stack up a whole bunch of added this, added the other, so on, all up here. If I were collaborating with other engineers, say other engineers were working on other bits of the simulation, I would be in a feature branch at this point because I wouldn't be pushing it until I had finished adding all the instructions in the 8080. But single developer, small project, trunk-based development works just fine. So, one last check. Here's our benchmarking results so far. We are not benchmarking the 8080 instructions yet. So these numbers still look good. I am confirming that I am running with OFast. Debugger symbols are turned on, but that doesn't seem to slow down our benchmarks much, so that's good. Yeah, I think so. So we're good. I think that's going to be it for this session, and I will see you in the next one when we start work on whatever the next thing is. There you go. So be sure to keep it small, keep it fast, and